So in the first problem, we have the walls of a refrigerator
Okay.
are typically constructed by sandwiching a layer of insulation between sheet metal panels. Consider a wall made from fiberglass insulation of thermal conductivity Ki and thickness Li, and steel panels, each of thermal conductivity Kp and thickness Lp. If the wall separates refrigerated air at T infinity I equal 4 degrees from ambient air at T infinity out equals to 25 degrees, what is the heat gain per unit surface area? Coefficients associated with natural convection at the inner and outer surfaces may be approximated by 5 watt per meter square Kelvin. So this is a typical problem, okay, of steady state conduction in a certain wall with different layers. Okay, so what is the strategy in such cases? What do we do? What is the easiest method to solve?
We do the
طبعا
thermal circuit.
الريزيستنس.
Yes, very good. We do a thermal circuit, and we know here that the direction of flow of heat transfer will be from which side to which side?
hot to cold.
Yes, so it will be in this direction. Okay, so it's like it's similar to a circuit in series where we have several resistances in series. Okay, we can start from T infinity 0. It is known equal to 25 degrees. Since we have convection between ambient air and this layer, we can start by saying we have a resistance to convection. Hala, can you tell me here we can put heat flux Q second or heat rate Q. Why we can put both? It doesn't matter here.
It doesn't matter because this is a plane.
Very good. It doesn't matter because it's a plane wall, so the area is constant over the wall. Okay, so if you put Q, which is the heat rate, then the resistance to convection will be 1 over H times A. Okay, and if you put Q second, which is in watt per meter square, you just put 1 over H. Okay, and now we have 3 layers. This is, do you want me to zoom in or you can see well the screen?
It's okay, it's good.
Okay, so we have 3 layers here, 3 layers of solid, and we know that through solids, heat will transfer by conduction. So we have to put 3 resistances for the first layer, L over K, characterizing first layer, L over K for the second, L over K for the third, and finally, we have convection to the outer, to the inner side, 1 over H, okay? And what is the first unknown to start with? Whenever we draw this circuit, what can we calculate?
Doctor, may you repeat your question?
Okay, once we draw this circle, okay, this circuit, what can we calculate now? We have this figure, okay?
Q second.
Q second, very good. So all we have to do is to say that Q second is delta T, where T higher minus T lower. So here, since heat rate is propagating in this direction, we do T infinity out minus T infinity in over summation of resistances. Okay, and once we do this, what is the next step? Now, what can we calculate?
The temperature in any point we want.
Very good. We can now calculate the temperature at any point of interest. Okay, if you are not interested into calculating all temperatures, for example, if I just ask for the temperature here at this point, I can apply Q second between this point and T infinity out, and then I divide by these 2 resistances, or I can apply between this point and T infinity in and consider the summation of these 3 resistances. Okay, So I can, depending on what I want to find, I can decide to apply Q second between any 2 points of my circuit. Okay? Any question on this? Okay, now in this problem, a house has a composite wall of wood, fiberglass insulation, and plasterboard as indicated in the sketch. On a cold winter day, the convection heat transfer coefficients are given, and the total wall surface area is 350. So here, of course, it's similar. So it's similar to the previous problem, but we'll do some analysis if you want on the dominant resistance. So we can draw an electrical circuit, same thing. We have 5 resistances, 2 convection, 3 conduction, and we know how to calculate the rate. Now, they asked first to determine the total heat loss through the wall. We can do this, okay, as we did in the previous problem. Then they asked if the wind were blowing in a violent way, raising HO to 300 watt per meter square Kelvin, determines the percentage increase in the heat loss. So here we want to investigate, if you want, when we have good insulation, this means that the heat loss will not be affected a lot by increase in convection. Why? Because if we do good insulation, the dominant resistance will be the resistance in the solid material. So even if the wind will blow in a very violent way, we will still have the increase in heat loss will not be very high. And this is the importance of insulation because it will allow to reduce the effect of outer climate. We can see this in this problem, okay? Let us compare together the values. So first, you draw your circuit as usual, and you can get the total resistance. And here you can compare, if you want, resistances values, okay? You have the convective resistances, and you have the conduction resistances. So whenever if you want, conduction is dominant, if the conduction resistance is dominant, this is a good sign of insulation, okay? Because even if the convective resistance, let's say, will be reduced, okay? Because when you increase, if the wind will be very violent, H will increase and the resistance of convection will decrease, okay? So this will reduce the total resistance to heat loss, and then the heat loss will increase. So when we reduce our convection, we expect to have Q second higher, okay? But if we have good insulation, the increase of H will not affect a lot the total resistance. And this is what we want to prove in this problem. Okay, so here just it's if you want, it's an application problem to show you that when you put good insulation properties, even if you the convective coefficient will increase, you can limit the value of the heat loss. Okay, so let us compare in numbers. If we consider the first scenario where we have low convective coefficient, the loss rate was 4.21 kilowatt. And now H increased a lot from 60 to 300, so times 5, okay? But if we look at the variation of the total resistance, this is what we care for, the effect on the total resistance. So only the total resistance decreased only by 0.5%, which is very good. Because since we have good insulation, the conductive resistance is the dominant one. And in this way, even if we have a very high increase in HO, the effect on increase of loss will be very small, okay? So this is the importance of selecting an appropriate material for insulation with good resistance properties, okay? Any question on this?
No.
Okay. Okay. Another problem, approximately 10 to the power 6 discrete electrical components can be placed on a single integrated circuit with electrical heat dissipation as high as 30,000 watt per meter square. The chip, which is very thin, is exposed to a dielectric liquid at its outer surface with convective coefficient given and T infinity outer given, and is joined to a circuit board at its inner surface. The thermal contact resistance, you remember what do we mean by the thermal contact resistance? So whenever you have two surfaces that are joined to each other, okay, we can have some, it's not a perfect match between them. We have, let's say, some roughness effects, which will lead to small voids between them, and this will create an additional resistance that we call contact resistance. The value of this resistance is 10 minus 4 meter square Kelvin per watt. Look, from the unit, you can know if this is R or R second, okay? Tell me, what is the unit of R, the resistance? No need to memorize it. Go back to the definition. What is the flow rate, Q? It's delta T over resistance, okay? So in case I am dealing with rate, this is in watt, this is in Kelvin, so R will be in Kelvin per watt, okay? While if I want to talk about R second, so this is the unit of R. While if I have Q second here, then I will have here R second. The unit of Q second is watt per meter square. And the unit of R second will be then meter square, okay? So R will be in meter square per watt Kelvin, okay? So times Kelvin per watt. So here, since the unit is meter square times Kelvin per watt, okay? So this means that we have R second. R second is given and not R, okay? Now, the thermal contact resistance between the chip and the board. So we have here at this level a contact resistance between the two, okay? And the value is given. And we know that the board thickness and thermal conductivity are also given. And the outer surface of the board is exposed to ambient air, for which Hi and T infinity are also given. So in this problem, okay, we have everything as usual. And we have propagation of heat from higher temperature to lower temperature. So here also, okay, we can determine the direction of heat transfer depending on the variation between T infinity in and T infinity out, okay? And in this case, we need to check if we have generation or not. If they mention anything about possibility of generation. So if we compare first the values of T infinity out and T infinity in, they are equal, okay? They are equal. This means that, of course, here we have a certain generation. And this is why they told us that we have an electrical heat dissipation of 30,000 watt per meter square. Okay, so here it's not like the previous problems. We don't have one direction for heat flux. Okay, already T infinity in equal T infinity out. So if we don't have generation, nothing will happen. In steady state, we'll have the same temperature everywhere because no delta T. Okay, but even if we have delta T, between the inner and the outer side, we should check if there is generation or not. If there is no generation, we'll always have heat transfer from the hotter to the cooler side. But if we have heat generation, then what will happen? The generated heat will be dissipated in two directions, okay? So here, one part will be lost, let's say, to the upper side, and one part will be lost to the lower side, okay? And here we need to draw appropriately the thermal circuit. What is new here? Can you tell me how we can consider this? We know that in generation in general cannot be, is not presented in a resistance system unless we consider it as it's a source, okay? It's a source within an electrical circuit. So we can consider at the point of generation, we consider it, here it's a point. Why we can deal with it as a point, the generation here? Who can tell me?
معناها عم بشتغل الكيو دبل دوت.
ما في thickness دكتور.
Very good. ما في thickness. يعني the heat dissipation is through a very thin layer, okay? Through this layer here. يعني they said that we have a heat dissipation per meter square, okay? So they didn't at the chip level here. Just at the chip level at the surface if you want, okay? Here, it's exactly at this point. So since, because it's very thin, so since the chip is very thin, okay, we can consider that this heat generation is at a point, okay? So we can consider that we have just a temperature Tc, okay? And this is why they didn't give us any thickness. So we can they neglected the thickness of the chip. They said that the thickness of the chip can be negligible, okay? That's why they didn't give you, if you want, thickness and conductivity of the chip, because we are assuming that it's a very thin layer. So we can consider that at chip level, we have just Tc, okay? And we have heat, this heat generation from the chip will be dissipated in two directions. One part will be dissipated upward, okay? And another part will be dissipated downward. So we can consider here that this is a source term. So we have at this level, okay, we can put Q second C that is generated, and it will be dissipated in two directions. One towards the outer side, okay? Now, can you tell me, towards the outer side, what is the resistance only? What is the resistance towards T infinity out? Yes,
It's
convection.
resistance by convection.
Exactly, only by convection. So I can, and since I'm dealing with Q second, I should put our second convection, which is 1 over H out, okay? While from the other side, okay, from the other side, what are the resistances that I will face? Let me clear here a little bit. Okay. So what are the resistances that I will face from this side? I have first...
Conduction.
Yes, first, which conduction of contact resistance? So I have the resistance to conduction due to thermal contact. Then I have the conduction resistance of the board. And finally, I have the convective resistance from the inner side, okay? So if I want to illustrate my thermal circuit, it will be of this shape. So I have a flow This is a source term, which is the generation, that will be divided into two parts. One towards the outer side with only a resistance to convection, and one to the inner side that is opposed first by the thermal contact resistance, then by the conduction resistance of the board, and finally by the inner convection. And then here, the equation that I will write is what? You have a flux that will be divided into two parts. So your equation is Q second generated is equal to Q second N plus Q second out. Okay. So this is all what you have to do here. And what is the only unknown here? You know T infinity inner, you know T infinity outer, you have all properties, okay? Your only unknown is the temperature, Tc, okay? So this will allow you to solve for Tc. And once you get Tc, okay, if I tell you what is the flux that will go out, what is Q second out? How to calculate Q second out now? Q second out is flowing in which resistance? If you look at your figure, okay, it's flowing in the convective resistance. So you can say that already you expressed Q second out here. So when you expressed Q second out, you said it's Tc minus T infinity out over 1 over H0. So this is your Q second out. And when you calculate Tc, you can come back to this term and replace Tc by its value. So if you replace Tc by its value, okay, then you can find the value of Q second out. While to calculate Q second N, okay, or you do now the difference, Q second N is Q second generated minus Q second out, or you evaluate this term because now you have Tc. So Tc minus T infinity inner over summation of these three resistances, because Q second N is flowing from Tc to T infinity N. So I have three resistances, okay, that I should overcome. So Q second N is equal to Tc minus T infinity inner over the summation of these three resistances, okay? So whenever you have generation, just pay attention. You don't have whenever the generation is between two media, okay? You cannot say you have a circuit in series. You need to put appropriately the source term and divide it in your circuit, okay? Any question on this problem?
No.
No.
Okay. Now, here it's similar, but now we are applying, if you want, other type of coordinates. So depending on the geometry, you can decide if you work with Cartesian coordinates or cylindrical coordinates. So here also we have a thin electrical heater that is wrapped around the outer surface of a long cylindrical tube whose inner surface is maintained at a temperature of 5 degrees. The tube wall has inner and outer radii of 25 and 75 millimeter respectively, and a thermal conductivity of 10 watt per meter Kelvin. The thermal contact resistance between the heater and the outer surface of the tube is given to be R second equals to 0.01 meter Kelvin per watt. And the outer surface here, it's R prime, not R second, okay? Why it's R prime? Because we said the unit of R second is meter square Kelvin per watt, okay? While if the unit is meter Kelvin per watt, this is R prime. So this is a resistance per unit length. Okay, so from the unit you can know what is the resistance given. The outer surface of the heater is exposed to a fluid with T infinity minus 10 degrees and a convective coefficient H equal to 100 watt per meter square Kelvin. Determine the heater power per unit length of tube required to maintain the heater at a temperature T out of 25 degrees. Okay, so here, what we want to do in this problem is to determine what is the power per unit length that should be provided, okay? Determine the heated power per unit length of tube, which is required to maintain the heater at T0 equal 25 degrees. So we need to calculate now what is Q prime. This is the question, okay? We need to provide a certain amount of heat in order to maintain this temperature here at the heater T out temperature at 25 degrees. So this is the purpose, okay? And since we have to maintain fixed temperatures, we have here a steady state application. So all we have to do is to draw the thermal circuit and do the analysis. Now, as usual, okay, you should check if you have generation or not. Here we have a generation from the electrical heater. So this is the source, Q prime in watt per meter, okay? And since we have cylindrical coordinates, then we need to use, of course, resistance to conduction. So we know that the resistance to conduction from the coarse material is ln R2 over R1.
R out minus R.
Exactly, R out over Rn, okay? Divided by 2 pi KL. But here we don't have R, we have R prime. So what do we remove? So this is 2 pi K times KL. To get R prime, what do we remove?
L.
L, very good. We just have to remove L. Then we will draw a circuit with resistances R prime and with heat rate per unit length Q prime, okay? Now, what do we have in this problem? They told us that we have a contact resistance between the heater and the outer surface of the tube. So this is the tube outer surface here, okay? This is the outer surface tube, and between the electrical heater and this outer surface, they said that we have a contact resistance, okay? And they gave us what is the temperature to maintain at the outer side of the tube, and at the inner side, the maintained temperature is 5 degrees. And we want to solve for the value of Q prime, so we need to draw the circuit. This is a source term, okay? So this source term will be dissipated in two directions. One part to the outer side and one part to the inner side, okay? And here, first, to the outer side, what is the type of resistance faced?
Convection.
Convection only, okay? While to the inner side, you have first the contact resistance, okay? Then you have the resistance of the tube. Do you have convection here from the inner side? Did they give you any convective conditions, or they just gave you the temperature
No.
here? No. So because they gave you the
Only
temperature at the inner side of the tube, no convective resistance. You just have two conduction resistances, the thermal contact one and the resistance of conduction in the tube, okay? So now we are ready to draw our circuit. Okay, so this is the generation term. Let us clear, okay. This is the generation term. We have dissipation from this side by convection to the outer side. And here, keep in mind, all resistances are R prime, okay? So R prime convection is what? It's 1 over H times the area per unit length. For a cylinder, what is the lateral area of convection? From the outer side, okay, the lateral area is perimeter, which is pi d0, times the length of the cylinder, times L, okay? But since I want per unit, the area per unit length, so I need A prime, then I remove L, okay? And I have here 1 over H pi d out, okay? While from the inner side, I have first the resistance to conduction, the thermal resistance, followed by the resistance to conduction, both expressed per unit length. Okay, R prime is already given per unit length because of the unit that we have seen together. And for the resistance to conduction per unit length, we said it's ln R out over Rn divided by 2 pi k. And in this equation, T0 is given, okay? And Tn and T infinity also are given. So here, the unknown, if you want, is Q prime. We need to calculate Q prime. So we just have to say that Q prime is equal to, it will be divided into 2 fluxes, per 2 rates per unit length. Q prime equal Q prime A plus Q prime B. And for Q prime B, it's just T0 minus T infinity over the outer convection resistance per unit length, while Q prime B is delta T, which is T out minus Tn over summation of the 2 conduction resistances per unit length. And then we will obtain the value of Q prime, okay? So once I get the value of Q prime, I can solve now for what is unknown. Yani when I get Q prime, okay, I solve for what should be the heat power supplied per unit length in order to maintain the temperatures as required at 5 and 25 degrees. Now, if they ask you, for example, what is the percentage lost, what is the percentage dissipated to the by convection, you can evaluate this term. If you evaluate the convective flux per unit length, okay, and you divide it by the total one, you can find what percentage will be convected out and what percentage will be conducted to the inner side. Okay. Question on this?
No.
So you can see that the ideas will be repeated, okay? So you just have to know how to draw the circuit, how to identify your unknowns and write the equation which will allow you to solve for your unknown. So in this problem, we have that the energy transfers from the chamber of the eye through the cornea varies considerably depending on whether we have contact lengths or not. We want to treat the eye as a spherical system and assume the system to be at steady state. So here, this is a problem on spherical coordinates. And as I told you in the exam, I will give you an appendix. So whenever you have spherical coordinates, you can go to the appendix to see what is the resistance in case of a spherical coordinate, okay? And assume the system to be steady state. So we can work with the thermal circuit. The convective coefficient H out is unchanged with and without the contact lengths in place. The cornea and the lengths cover 1/3. This is a small trick, okay? We don't have a complete sphere. We have just 1/3 of the spherical surface area. Okay, so then what do we have to do? If the area, we should go back to the definition. Okay, you know that if the area is reduced, what will happen to the resistance? If I tell you, I can calculate the resistance for the whole sphere. Okay, now I am not dissipating heat from all directions. For my eye, I'm just dissipating in 1/3 of the area. So what will happen to the resistance?
It will be higher.